A student conducts a practical investigation in order to test whether the dissolution of solid ammonium chloride is exothermic or endothermic. The apparatus used includes a beaker, the salt, and a certain measuring instrument. The figure below shows the energy changes that occur when ammonium chloride dissolves in water. If I'm trying to work out the energy changes, what measuring instrument must be used in this investigation? And it would be a thermometer. What is the function of that instrument to measure temperature? You need to think through exactly what they're asking in each of these, because it's quite obvious when I say it, but you need to think what exactly is trying to be measured here. Will the reading on the instrument increase, decrease, or stay the same during the course of this reaction? This is a classic shape of an endothermic reaction, and therefore the temperature will decrease. Why? Because it's an endothermic. What is the potential energy of the reactants? There's the reactants, so it's going to be 50 kilojoules. Calculate the delta H for this reaction. Delta H is the difference between reactants and products, so it's 170 minus 50, and I land up with 120 kilojoules. Calculate the activation energy. That is going to be, you would think all the way from there to there. There we go, from the reactants all the way to the top of the activation curve. So that's 200 minus 50, and you land up with 150 kilojoules. Don't forget your unit each time, and draw a similar graph to show the effect of the addition of a catalyst to this. So we now need to just bring, let's try it like that, like that. So your energy hump is lower. What's important is that the reactant's energy is the same and the product's energy is the same. It's just that this energy hump is lower. An experiment is conducted at two different temperatures, T1 and T2, to investigate the relationship between the rate of a chemical reaction and the temperature of that reaction. The diagram below shows the Maxwell distribution curve for the experiment conducted at two different temperatures. Now we need to think about these Maxwell curves. This temperature looks higher, but actually the energy of the particles is, most of the particles have got lower energy than this one where most of the particles have got higher energy. Which temperature was higher, T1 or T2? T2, why? Because it has got more particles with a higher amount of energy. They then ask what is meant by this shaded area over here, and the shaded area tells me the number of particles that have enough energy to react, since they have more than the activation energy. The reaction between magnesium ribbon and hydrochloric acid is used in an experiment by some students to investigate the factors that influence the rate of a chemical reaction. The reaction that takes place is given. The diagram shows a basic setup for this investigation. I've got magnesium, some acid, and then clearly I'm collecting the gas in the syringe. This thing here is called a syringe. Lots of you called it lots of things. It's called a syringe. Name one apparatus measuring device not shown in the diagram, which is important. Whenever we're measuring rate, we're going to need to ensure that we are measuring time. So a stopwatch or a clock or something like that would be necessary. In 2 steps, describe the procedure the students should follow to measure the rate of that reaction. First thing is, and I decided not to give you a penalty on the marks of it, is you do need to ensure that this is properly sealed. So you need, but it looks like that in the picture already, so I didn't take away a mark. And then you're going to start the stopwatch, allow the reaction to take place, and when the rubber stopper stops moving, you're going to stop the reaction. Something along those lines for your 2 marks. In what way will the rate at which hydrogen gas is formed be affected if heat is added to the apparatus? It is going to heat is always going to increase the rate of the chemical reaction. Use the collision theory to explain your collision, at least your conclusion. The particles have got more kinetic energy. Whenever you talk about heat, you need to talk about more kinetic energy. And therefore, there will be more collisions. You had to use collision theory, so you need to get to the point of collisions as well. The next one, it is important that any experimental procedure has both accuracy and precision in its design. Altering one variable at a time and conducting a number of repeats of the same experiment are both methods of ensuring a fair test. Differentiate between accuracy and precision. This is just bookwork again. So, accuracy is going to land up being when you get close to the correct theoretical answer, whilst precision is when your answers come out in a narrow range. In an experiment, the students use 50 centimeters cubed of hydrochloric acid of known concentration and 25 centimeters cubed of the same hydrochloric acid diluted to 50 centimeters cubed with the distilled water. The graph which follows represents the results obtained. So this is the first one with the more concentrated, and this is the more dilute acid. State an investigative question for this reaction, and you would say something like, does an increased concentration result in a faster rate of reaction? Something along those lines. You need to. Or more, the volume of gas is produced faster with more concentrated acid. But it has to be a question. So, is the volume of gas produced more quickly with a more concentrated acid? You need to somehow have time, volume of gas, and the fact that there's different concentrations of acid in your question. What volume of gas was formed during the first 2 minutes of experiment B? 2 minutes is 120 seconds. So you're looking at experiment B and you go across. You need to give me a unit. It's 60 centimeters cubed. The next one, how much time elapsed before experiment A reached completion? Completion is that point over there. So it's 240 seconds. No one told you to convert it into anything other than that. Calculate the average rate of experiment A and experiment B. When you're calculating the average rate, you need to, the rate of the reaction is the gradient of the graph. So what we're going to do is we're going to say change in Y, which is change in volume, over change in time. And on average, what happened? So for experiment A, the change in volume was 120. And how long did that take? That took 240 seconds. So it's 120 centimeters cubed divided by 240 seconds. And that lands up being 0.5 centimeters cubed per second. For B, I'm going to also get to 120 centimeters cubed. But how long did that take? In experiment B, that took 360 seconds. So I now need to divide by 360 seconds, and I land up with 0.33 centimeters cubed per second. Which experiment, A or B, took place at the faster rate? Refer to the shapes of the graphs to give a reason for your answer. So it was experiment A that took place at a faster rate. I can see that from that reading. But in terms of the shape of the graph, that is because I have got a steeper gradient. They want me to refer to the shape of the graph. I need the shape of the graph. Now we have got our classic question about with rice tables and that sort of thing. So it has been said that more sulfuric acid is produced in each year than any other chemical. It is used in every industry, and the amount that is used is a measure of the economic growth of a country. One of its main uses is to make fertilizers such as ammonium sulfate. Sulfuric acid is manufactured by the contact process, which is familiar to you, in one of the stages of the contact process, sulfur dioxide reacts with oxygen to produce sulfur trioxide. Here's the reaction. And we can see quite clearly over here that delta H is less than 0, so that is an exothermic reaction. We've got 3 gas moles over here and 2 gas moles over here. So the temperature and pressure are increased respectively. State the effect on each of the changes in the rate of the reaction, the amount of sulfur trioxide produced, and the Kc value. So an increase in temperature. First thing that's going to happen is it is going to increase the rate of the reaction because the particles will come closer together. Then we've got what will happen to the yield if I increase temperature? Increase in temperature on an exothermic reaction is going to decrease the yield. And if it decreases the forward reaction, temperature does change Kc, so it's going to decrease Kc. Why? Because I am going to have concentration of products over concentration of reactants, and therefore if my products decreases, so does my Kc decrease. Then we've got an increase in pressure. What's going to happen? I am going to the rate of the reaction once again will simply increase, because increase in pressure means that the particles are close together. What's it going to do to the SO2? As I increase the pressure, it will go to the side with the least gas moles, so that will also increase. And Kc is not affected by change in pressure, it is only affected by change in temperature, so that stays the same. State Le Chatelier's principle. Le Chatelier's principle, once again, is just bookwork, so let's get that down. If a system at equilibrium is disturbed, sorry, that's not but it's by a stress, the equilibrium position will adjust so as to minimize that stress. Certain amount of SO3 is sealed in a container. That should be a subscript 3, but anyway, the following equilibrium is reached at 450 degrees centigrade. And we are given the exact same reaction, except now it's written in reverse. After 8 minutes, the temperature is lowered to 300 degrees centigrade. The graph shows the changes in the reaction over a period of 12 minutes. Write down the reaction represented by the dashed line. Well, the forward reaction is always the one that starts higher, and therefore it must be the reverse reaction. And therefore, either you could have just told me it was reverse, which is acceptable, or you could have written it the other way, which is 2SO2 plus O2 gives me 2SO3. To find dynamic equilibrium, it is when the rate of the forward reaction is equal to the rate of the reverse reaction. When does this reaction reach equilibrium for the first time? Over here, at 4 minutes. Is the reaction represented by the dotted line endothermic or exothermic? Given explanation. Well, we told something happens over here, and we've lowered the temperature. Lowering the temperature seems to have had less of an effect on the dotted line than on the solid line. So there was a small effect on the dotted line. In other words, the dotted line was favored. So forward, at least reverse, was favored. So if the reverse is favored, that means that the reverse must be, if it was from a lowering of temperature, the reverse must be exothermic. Is the reaction represented by the dotted line? We are talking about the reverse reaction, so it is exothermic, and the reason is given above. When the temperature drops, there is the reverse reaction is favored. What is represented between 10 and 12 minutes over here? We have got a new equilibrium position at that point, because obviously they both have the same rate once again. Redraw the above graph from 10 minutes to show the effect of on the rate of both reactions if a catalyst is added. Now remember, catalyst doesn't favor forward or reverse. All that's going to happen is it's going to increase the rate of both reactions. So you start with your solid, it goes up a bit and re-equilibrates. You use your dotted, it does exactly the same thing and re-equilibrates. So that is the kind of shape you are looking for. You would need to have labeled your graph with a rate and a time, and you would have had to have said 12 minutes in order to get all of your marks.